Everybody, my name is Edward Hutter. So over the past decade or so, there's really been this challenge to the notion that designing algorithms to reduce computation is the best approach to increase performance on modern architectures. Modern architectures are seeing an exponential increase in peak performance relative to the peak network injection rate, and this fact has enlarged the algorithmic search space to include those algorithms that focus on reducing communication and synchronization, even at the expense of extra computation. So throughout this talk, we're going to be utilizing the simple alpha, beta, gamma cost model, where alpha is the cost to send a message over a network. Alpha is the cost to send a 0-byte message. Beta is the cost to move a byte of data into the network, and gamma is the cost to perform a floating point operation with register resident data. And so, as mentioned, the trend is that alpha is decreasing exponentially slower than beta, and beta is decreasing exponentially slower than gamma. So there does exist a lot of communication avoiding algorithms that are present in numerical libraries, maybe not Scalability, but they do exist. One important matrix factorization is rectangular QR factorization, and that there is no communication optimal algorithm for that present in numerical libraries. So the goal we're going to look at today is a QR factorization algorithm that prioritizes minimizing communication and synchronization. And so our team uses Blue Waters to assess the scalability of new algorithms for numerical tensor algebra. And so I want to include this chart here. So this is the trends in architecture. I want to look at the machine balance in particular. So since 1997 up to this year, you can see that the machine balance on the right is decreasing exponentially almost. And so I want to highlight two architectures in particular, because these are the architectures we're going to test our QR factorization algorithm on, Blue Waters and Stampede2. We see that Blue Waters' machine balance is around 8 times higher than that of Stampede2. And through the lens of communication avoiding algorithms, this means that Blue Waters is not a great architecture to run these algorithms on. So if we want to increase the arithmetic intensity via communication avoiding algorithms, and an architecture like Stampede2 is probably the best architecture for that. We're going to see how this difference in machine balance affects the performance. Right, so as mentioned, we want to design algorithms with higher arithmetic intensity, and we want this to equate to higher performance on new architectures. Blue Waters is just not a favorable machine for this, whereas Stampede2 is. So there is this well-known trade-off with 3D algorithms in trading off extra memory footprint for asymptotically smaller communication. And so we want to introduce communication avoiding Chelsea QR2, which is a novel practical 3D QR factorization algorithm. It does extend the Chelsea QR2 algorithm to matrices of any dimension. It reduces the communication by this asymptotic factor quantity PM squared over n squared to the 1/6 versus known 2D algorithms like those present in Scalability. But it does incur trade-offs. It does perform around 2 to 4 times more flops than householder QR. The matrix must be sufficiently well conditioned, and it does require asymptotically higher memory footprint versus 2D algorithms. And so all algorithms will be analyzed along the critical path versus looking at the volume of communication. And so just this simple diagram for a communication routine, just such as a near neighbor exchange, the synchronization and communication will not be dependent on the number of processes, but for like an all reduce, the synchronization and communication will be dependent on the number of processes. So I want to sort of foreshadow these results for our algorithm versus Scalability on both Stampede2 and Blue Waters. And we can easily see that for a matrix that's pretty tall and skinny, so a ratio m over n of 4,096, our algorithm performs around 3.3 times better at 1,024 nodes or 65,000 processes. And it generally performs better starting at 8,000 processes. But if we look at, and that's on Stampede2, if we look at the performance on Blue Waters, our algorithm, even for this tall and skinny matrix, is not performing as well as Scalability, and this is sort of expected given that the machine balance of Blue Waters is around 8 times higher than that of Stampede2. If we look at increasingly wider matrices, we see that on Stampede2, our algorithm continues to perform better than Scalability on Stampede2. But then on Blue Waters, it's still we are still not outperforming Scalability, although that gap is getting increasingly small as we increase the number of processes, and this is due to the communication reduction as P increases. So another wider matrix, MRN equal to 64. Again, we sort of see the same trends here with the results on Stampede2 and Blue Waters, and then a row versus column ratio of 8, and then 1. So if we look at square matrices, we see that our algorithm really doesn't perform that well versus Scalability because of the computation overhead, and so the decrease in communication doesn't play that large of a role in the range of processes that we test. So we want to see where our algorithm fits into the existing QR factorization. So we start with Scalability's PGE QRF routine, which we benchmark against. And so this is a 2D algorithm, meaning that it is communication optimal, assuming minimal memory footprint. But it does incur a very large synchronization cost due to computing the householder vectors. And so there's n column vectors, so we see this n log p synchronization cost. That was improved with the communication avoiding QR algorithm because it uses tall and skinny QR to factor panels. And so that reduces the synchronization, but it does not asymptotically reduce the communication. So it's still a 2D algorithm. And then we look at our algorithm communication avoiding Schleswig QR2. It does asymptotically reduce the communication, so it can be considered a 3D algorithm. However, it does incur a higher synchronization cost and a higher memory footprint. And so there does exist 3D communication avoiding QR factorization algorithms in theory, some for square matrices, and then recently for rectangular matrices. However, there's been no results shown because these algorithms don't use practical building blocks, basically, and so our algorithm is the first practical approach that can achieve speedups on large machines. So QR factorizations can be basically put into 2 different buckets. One is a process of orthogonal triangularization, which is numerically stable, and then the other is a process of triangular orthogonalization, which has been shown to be numerically unstable. And so Schleswig QR2 falls in that latter category. It is not numerically stable in all cases, and there's many cases in which it can fail. If we compute A transpose A, the resulting matrix can be indefinite, infinite precision, and this may cause the Cholesky factorization to fail, and then we obtain a orthogonal factor Q with no accurate digits. And so the idea of Cholesky QR2 is that it leverages the near perfect conditioning of Q in a second iteration. Because as we can see, if A is perfectly well conditioned, then this algorithm is fine. And so this algorithm was shown to achieve superior performance on very, very tall and skinny matrices. And if we look at the difference in computation, we see that it can perform around 2 to 4 times as many flops as householder QR. But because, so here's a diagram of that algorithm. So a 1D processor grid is used because the matrix is is very tall and skinny, and then after a single all reduce, the matrix B can be replicated on every machine, and then the rest of the commutation can be done sequentially. And so it does reduce the communication of TSQR by a factor log P, and it does have a very simple implementation, and that's important. But I highlight two cost terms in red here, the communication and the computation, and it's clear that this is not going to scale for a square matrix or really any matrix that's not sufficiently tall and skinny. And so communication avoiding QR2, our algorithm parallelizes Chelsea QR2 over a three-dimensional processor grid, and this allows us to reduce the communication. So our algorithm leverages known 3D algorithms for matrix multiplication and Cholesky factorization, and it uses a tunable three-dimensional processor grid of dimension C by D by C, where C is the replication factor, root C is the communication reduction, and the number of simultaneous instances of 3D algorithms is D over C. And so the three computations are basically the computation of the grand matrix A transpose A via a sequence of collective routines, D over C simultaneous three-dimensional Cholesky factorizations on cubes of dimension C, and then D over C simultaneous triangular solves on cubes of dimension C. And so we obtain this tunable cost expression, and if we force each process to own a square submatrix, then this is how we choose the shape of the processor grid to support minimal communication. And so we can step through these cost terms again. One-dimensional Chelsea QR2 does not scale for arbitrary matrices. If you look at two-dimensional scale-up pack, it has a high signalization cost, which two-dimensional CAQR does improve, but it does not improve the communication. And so our 3D algorithm, it reduces the communication asymptotically. And so we factor n by n matrices with a variety of m and n to show the performance. And so we test on Stampede2 and Blue Waters, and we want to sort of look at how our algorithm's increased arithmetic intensity affects performance on these different architectures with different machine balances. And so we choose the most performant variants at each node count. We tune over a ton of different processor grids on scale-up pack and block sizes, as well as our own parameters of D and C in our algorithm. And in these performance numbers, we do match the computation cost of householder to obtain the performance numbers. And so these are the same results I showed, but it's sort of more, it's a deeper analysis. If you look at the M/N ratio of 4,096, we see that there's a computation overhead of about 2 times. And on Blue Waters, we start to decrease in performance, and we do increase in performance relative to scale-up pack as the number of processes increases. And on Stampede2, starting at 4,096 processes, we get better and better versus scale-up pack with a 3.3 times speed up at 65,000 processes. And so this sort of continues, this trend continues on Blue Waters and Stampede2, but as we decrease the ratio of m over n, our algorithm performs worse and worse because of this computation overhead of 4.25 times for a square matrix. So if we want to look at the breakdown again of communication avoiding Chelsea QR2 for Stampede2 versus Blue Waters, this is for the same matrix. We see that the commutation is higher on Blue Waters because of this machine balance difference. And so this is for a matrix with 500,000 rows and 2,000 columns. If we make it wider, we see the same thing, and then the gap is less pronounced as we increase the number of processes in the strong scaling study. So we see that communication avoiding Chelsea QR2 does improve the performance over Scalability on Stampede2 by around 3.3 times. But on Blue Waters, we don't perform as well, and that's to be expected. And so we do leverage current and future architectural trends because the machine balance is getting smaller and smaller with Sierra and Summit. And so this algorithm sort of motivates increasingly wide overdetermined systems, which is a critical use case in solving least squares and eigenvalue problems. We are looking into offloading computation to GPUs on the XK nodes of Blue Waters because these nodes have a higher arithmetic intensity, and so we expect our algorithm to perform better on these nodes versus the XC nodes. And so our study basically shows that communication optimal parallel QR factorizations can achieve superior performance and scaling up to thousands of nodes. We also developed the Cyclops tensor framework. This has been developed by Edgar Solomonic. And so many applications that this framework is used for include tensor computations, tensor completions, networks, quantum chemistry, quantum circuit simulation, bioinformatics. And so we want to thank NCSA and the Texas Advanced Computing Center for benchmarking resources, and I'd like to acknowledge the Department of Energy for my computational science graduate fellowship. Thank you.